Welcome to our presentation for an autonomous, low-cost, and portable lysimeter for use in a greenhouse system. Here is our design day poster, which outlines our objectives, design, process, and the final results. My name is Cassidy Campbell, and these are my team members. To give a brief summary of what a lysimeter is, it is used in greenhouses to collect data on the nutrient solution, pH, electrical conductivity, and the amount of water used by the plants. Monitoring those properties is essential for maintaining the proper environment for crop growth and resource allocation. This picture provided is the current system that we use in the research greenhouses here at the U of A, and it requires a great deal of manual labor each day. For the current system, you would have to take the pH and EC measurements using the handheld sensor for both the input solution container, which is the blue bucket, and the output solution container, which is the black tub. You also have to measure the amount of nutrient solution in each container to make the drainage calculation. You then would empty both containers into a drainage channel, which means the water would not be recycled. Pictured here is a sample data sheet that shows you how we manually collected the data and recorded it on paper. At the end of each week, the data would be transferred to Excel. You can see that this method of measurement and data collection is tedious and time consuming, so our smart lysimeter is designed to make this process much more efficient. Pictured here is an example of a commercial greenhouse lysimeter. Prices range from $15,000 to $20,000 and are used for higher scale operations, so it would not be suited for low to medium tech greenhouses. We gathered this information from our sponsor, and you can see that having a well-managed greenhouse with a functioning lysimeter increases yield and in turn increases revenue. If you consider a greenhouse with an area of 5,000 to 10,000 square meters, a poorly managed greenhouse without a lysimeter has a revenue ranging from about $288,000 to $924,000. While a well-managed greenhouse that utilizes a lysimeter has a revenue ranging from $825,000 to $2.6 million, which is a 30 to 40% increase. The manual measurements and data collection take about an hour per day and need to be executed every day of the year. With minimum wage at $12.80 in Arizona, the use of the smart lysimeter would save around $4,672 in labor costs, not including fringe benefits. Here's a side-by-side comparison of the current system and then our smart lysimeter system. The current system requires human presence and is time sensitive, while the smart lysimeter is autonomous and has time data collection. The current system only takes one data point per day, while the smart lysimeter takes data points every irrigation cycle. The current system has manual dumping of solution, while the smart lysimeter has automated dumping. The current system, the drainage solution is not reused, while in the smart lysimeter system, the drainage solution is recycled. And then as for the current system, there's manual data entry, and then the smart lysimeter is automated data entry. And the current system is also 2 units, which isn't very portable, and then the smart lysimeter is 1 portable unit.
The above illustration walks through the sequence of events that occur once the lysimeter is turned on. First, the nutrient solution flows into the tank through the inlet piping. It enters each side of the tank and into the first sump where the pH is measured first. The water then flows into the next section where the electrical conductivity and fluid level are measured. The data is then displayed on the LCD screen. Lastly, the water is pumped out of the system through the outlet piping. Here is our system architecture, starting with our overall system, the smart lysimeter at the top. The next level are our 3 subsystems, the first being the computer assembly, followed by the sensor and circuits array, and lastly, the collection tank and drainage assembly. The necessary components for each subsystem are listed below in the final level. Here are our top level functional requirements that are based on both the given sponsor requirements and the overall project objective. Number 1, the system shall be autonomous, portable, and low cost. Number 2, the system shall collect and hold the input nutrient solution and the drainage nutrient solution. Number 3, the system shall measure the pH and electrical conductivity of the collected solutions. Number 4, the system shall calculate the drainage rate. Number 5, the system shall record all the collected and calculated variables in the microcontroller/computer memory. Number 6, the system shall pump out the nutrient solutions to the drainage channel. Number 7, the system shall present the data on the microcontroller LCD screen for operator viewing. And lastly, number 8, the system shall work in both commercial and research greenhouses.
Here we have the block diagram for one half of the system. The other half of the system is identical. Data is collected within the tank, and each of the sensors sends the data to the Raspberry Pi microcontroller. The water pump is controlled by the Raspberry Pi. The system is powered by a standard wall outlet and displays the data via user interface on an LCD screen. Here we have the graphical user interface. Displayed on the screen is the home screen that you would see if you were to pick up the LCD screen. Next, we will toggle to the pH data, where you can see the most current pH data, as well as maximum and minimum optimal values, as seen by the red lines, to quickly determine whether or not the data is within those values. The same can be shown on the EC data and drainage data. Next, moving to system health, the operator can quickly determine if all of these sensors are in good working condition. Finally, moving to the settings, this allows the operator to change the data collection frequency, pause the data collection for maintenance, and find replacement parts information. Along the bottom, there is a button that allows the operator to select for emergency shutdown. Next, we have the program flow. The software begins with an initialization of 3 threads: the timer thread, data collection thread, and GUI thread. Once the data collection thread has been initialized, it will remain in idle mode until the timer thread, which is synchronized with the irrigation cycles, sends an interrupt signal to trigger the data collection event. After the data is collected, the GUI will update with the latest data. Next, we have the verification process, which we developed to be multi-leveled and begins by testing the software to ensure that it is functioning as expected by the user. Then the sensors will be connected to the microcontroller, and each sensor will be individually tested to ensure accuracy and compatibility with the software. Next, the sensors will be integrated into the collection tank with the water pumps and piping to allow for a full system test. Finally, any necessary adjustments were made, and we moved on to the final acceptance testing. Here we have the budget analysis. We've included the bill of materials for 1 unit lysimeter, the cost of the prototype materials and team shirts, and estimations for the design day presentation materials. The sum of these costs are $2,255, leaving us with a budget surplus of about $1,745. Lastly, we would like to thank our sponsors, Murat Kassira and Mike Mason, for their continuous advisement. And we'd like to thank our mentor, Patrick Caldwell, for his support during our project.